Hello. You know, a lot of times people think learning how to use computational chemistry software is like learning how to use Microsoft Excel or something like that. It turns out it's really much more complicated than that because quantum chemistry software is based on very complex equations, and sometimes the equations are not numerically stable, sometimes they're very hard to code up, so there are a lot of things that can go wrong. And the competent user has to know a little bit about what some of those methods are and what kinds of things are likely to go wrong and then how to work around that. So today what I'd like to do is tell you a little bit about how to choose methods appropriately and how to look out for common problems and maybe what to do about that. So let me share some practical advice for how to set up quantum chemistry calculations and how to monitor if they're doing what you want. First off, the choice of basis set. This can be really critical. And STO3G, although it's useful for pedagogical purposes, is really too small for any actual application. What you want instead is some kind of polarized double zeta basis set for most normal calculations. So I recommend the Popal 631G star, also known as 631GD, or 631G star star, also known as 631GD comma P. You're probably going to get quite reasonable results with these basis sets. They may be better than the newer CCPV-DZ basis set, which for this size of basis set is often not giving results as accurate as the older 631G star star. On the other hand, if I need to go to higher accuracy than I can get with polarized valence double zeta, then in that case I don't recommend the Popal 6311G family. Those have now become kind of obsolete for triple zeta calculations. Really, the Dunning CCPV-TZ is a superior basis set in the triple zeta range. If you want to do benchmark calculations, then you're going to want to go to a quadruple zeta basis set, or even more, depending on what you're doing. But that requires an extra level of expertise if you're talking about benchmarking computations. Don't forget, if I want to do calculations on anions, then I really need those diffuse functions denoted by AUG if it's a Dunning correlation consistent basis set, or by a plus symbol if I'm doing the Popal basis sets. I'll need diffuse functions for excited states as well, especially if they have a Rydberg character to them, which would be a lot of excited states. Or if I had dispersion-bound complexes like a methane dimer or something, I would need diffuse functions. If I'm in an element in the periodic table that is lower than neon, I may need to use this plus D version of the correlation consistent basis sets if that's the family that I've chosen. In the original design of the correlation consistent basis sets, the D functions that were chosen were not quite tight enough. And so this was later fixed with a revision to the basis sets where an additional tighter set of D functions was added, and that's denoted by this plus D. So if I'm looking at sulfur atoms, for example, I really ought to be using this plus D version of the basis set, which is newer and more appropriate. And then finally, if I'm in group 1 or group 2 for the alkali or alkaline earth metals, then I probably want to correlate the N-1, the lower shell of electrons, and that's because the valence shell and the next lower shell are typically very close in group 1 and group 2. And if I do want to correlate those, and I'm doing some post-Hartree-Fock method, for example, then I need the correlation consistent polarized core valence XZ basis sets where the C denotes core correlating functions. And I need functions that are the appropriate size if I'm trying to get these core valence correlation effects in. I would also want to use those if I'm just going for high accuracy and comparing to some spectroscopic experiment. Now, on terms of the choice of method, theoretical method like Hartree-Fock or DFT, what's my advice? I would say always pick DFT over Hartree-Fock. Your computational costs are going to be similar. If I don't have hybrid functionals, then the cost of DFT can actually be cheaper. If I do have hybrid functionals, then the cost of DFT won't be much more than Hartree-Fock, but the DFT is almost always going to be more accurate if I have some reasonable choice of functional. In general, I think you'll find DFT is better than Hartree-Fock and similar in quality to MP2, although sometimes the quality is better than MP2. And then CCSD would be next, and CCSD Princess T would be next. So you can kind of pick along the scale depending on what accuracy level you're shooting for. I don't recommend the Moeller-Plesset perturbation series unless you're stopping at the simplest MP2 level. Recall that the cost of MP2 is order into the 5th, and CCSD is order into the 6th. So MP2 can make sense because it's cheaper than CCSD and more accurate than Hartree-Fock. But going to MP3, MP4, MP5 isn't recommended because the series doesn't necessarily converge. If you need more accuracy than MP2, use couple cluster instead because it's going to be a more robust method. If you're looking to tackle a unimolecular bond dissociation or diradicals or partially filled D shells or F shells, these can involve electronic near degeneracies that might require a method like a multi-configurational SCF or a complete active space SCF or CAS-PT2. There, MP2 or even CCSD or CCSD Princess T may not be appropriate depending on the situation. And unfortunately, DFT isn't any better. And I see a lot of papers where people go ahead and use DFT, say, for diradicals, even though they're essentially based on a single Slater determinant reference if you're doing cone sham DFT, and so you have sort of half the wave function that you want, which is a dangerous situation. And similar comments about MP2 or even couple cluster. If I want to study weakly bound complexes, so-called van der Waals complexes like methane dimer or something like that, Hartree-Fock, semi-empirical methods, standard density functional methods are not appropriate for those because they don't have the appropriate correlation, long-range correlation that you have in London dispersion forces. Remember, London dispersion forces have a fluctuation in the electron density on one monomer that creates an instantaneous dipole moment, and that instantaneous dipole moment induces a complementary dipole moment on the other monomer. So this is the correlated motions of electrons. You do have electron correlation terms in density functional theory, but they tend to describe very short range interactions. If you're at longer range, say 5 angstroms or longer, DFT doesn't see out that far if it's a standard DFT. There are some non-local correlation functionals like VB10 that would be appropriate in a situation like this, or practically speaking you could use the -D style corrections popularized by Stefan Grimme and others that will fix things up. But your run-of-the-mill B3-lip, for example, is not appropriate in a situation like that without some kind of cleanup. Now, it's useful to look through your outputs and make sure everything is behaving the way it should. And the very first thing to check is that your SCF procedure, whether you're doing Hartree-Fock or DFT, actually converges. You remember it's an iterative process where I guess a density and then I iterate and iterate, and the energy is hopefully going down, down, down. And it should take, 10 or 20 steps and then converge. And if this doesn't converge, this will cause many, many problems down the road. A lot of times I have students come to me and say, my geometry didn't converge. And I'll say, well, did your Hartree-Fock converge? And they'll say, well, I don't know, I didn't look. And I'll say, well, check that. And they'll look and say, oh yeah, no, the Hartree-Fock didn't converge. Well, of course, if your Hartree-Fock doesn't converge or your DFT doesn't converge, then anything after that, like getting the gradient of that, also won't converge. So you have to start at the beginning and see, does your self-consistent field procedure converge? And if that works, then you can look at things that come after that, like the gradient of that or the MP2 on top of that. Suppose your SCF doesn't converge. What can you check? Well, the very first thing I would check, which I didn't even put on the slide, is to make sure that the geometry you fed it is a reasonable one. If you put in an unreasonable geometry, suppose you freehand draw some molecule in WebMO and you forget to clean it up before you hand it off to a quantum chemistry program, well, you might have garbage, bond lengths or bond angles, and the code just can't fix that. It's too late if you start off with something that's really far off. But assuming you have a reasonable geometry, then what else can I check to try to make the SCF converge? Well, the brute force solution is to just give the SCF more iterations. Most programs have some keyword you can specify to change the maximum number of iterations. A lot of times it'll default to about 50 or so. You could give it 100. I don't necessarily think this is a great way to solve the problem because, as I say, it's brute force. But if you're pretty close and it just needs 5 more iterations, then just do that because that's very simple. If it's going to take a lot of iterations, then it's a sign something isn't really set up very well. You might frequently be able to solve this by converging the equations in a smaller basis set. Maybe the STO3G that I don't recommend for normal applications, but it's great for initially converging an SCF in a very quick and simple way. And then you could use the density from that as an initial guess for your real calculation using a bigger basis set. And a lot of programs have some keyword where you can specify an initial convergence in some small basis set followed by the real calculation. And I recommend this. This is a generally robust strategy for getting the SCF to converge. If I have an open shell, maybe it's a triplet state or diradical or something, I can sometimes add a level shift to the calculation, and that can help. Sometimes it's useful to run a calculation on the corresponding closed shell version of that molecule and then save those orbitals and then load those up as guess orbitals for the open shell calculation. Very practically speaking, although some people prefer restricted open shell Hartree-Fock to unrestricted Hartree-Fock for theoretical reasons, nevertheless, in my experience, unrestricted Hartree-Fock UHF calculations tend to be a little easier to converge than ROHF, and for that reason I typically like UHF for open shells just because it's easier to get the convergence of the wave function. Alright, so here's some other things you should be wary about as well. If you are doing a geometry optimization, say before a vibrational frequency calculation, be sure that that geometry optimization actually converges. Otherwise, you don't have an optimized geometry, and you want an optimized geometry if you're going on to do vibrational frequency calculations or thermodynamic analysis. You want to do that at an optimized geometry. If the geometry does converge, you might want to check that it's a good convergence to an actual minimum, assuming you're looking for a minimum. And you can do that by running a frequency calculation. And if you are trying to find a minimum, you want to verify that you have all real vibrational frequencies. If you do, then you're at a minimum, and that's great. If you get an imaginary frequency, it's a sign you're not at a minimum, and then you might want to try to re-optimize. Of course, if you're looking for a transition state, you do want exactly one imaginary frequency, and you can check that you get that. If you have more than one imaginary frequency, it means you're off a little bit in trying to find the transition state, and you might want to try to tweak your geometry and restart the transition state search. Sometimes you can get very small imaginary frequencies, like imaginary 10 wave numbers, whereas you're expecting a 0 for that mode because it's supposed to be a translational mode or something. If that's the case, if it's a small enough number, you might just ignore it. But if it's a little bit bigger number, 10 or 20 or 40 wave numbers, that's a sign you're not quite there. And so a lot of times you can clean up this annoying little numerical noise by tightening up the convergence on your energy or on your integrals or on your geometry optimization. And a lot of times then those tiny little imaginary frequencies will just go away and be replaced by the zeros that you're looking for translations or rotations. And so you do want to check if that you have 3n minus 6 vibrational modes, or if it's a linear molecule, 3n minus 5 vibrational modes, where you get, if you're looking for a minimum, real frequencies that are not imaginary. Okay, let me say a little bit about symmetry in optimizations. If I start off an optimization with a certain point group symmetry, like water has equal OH bond lengths, and if I start an optimization with that, then I'll find that the optimizer will keep those bond lengths the same. At least that's how it normally works. And that can be good or bad depending on your goals. If it's a water molecule, you want to keep the OH bond lengths the same because they are the same in the real molecule. On the other hand, if it's some unknown molecule you're not familiar with and you're optimizing the geometry and you guess certain coordinates have equal values, you may or may not be right about that. And the program will stick with whatever symmetries you give it. And that's simply because quantum mechanics will inherently see the symmetries of the geometry you give it, and that will turn into symmetries of the wave function and symmetries of the forces that act on the atoms. Now, suppose you optimize a molecule and you guess a symmetric geometry and it optimizes. Do you know if it really has that symmetric geometry or if it's just stuck with it because that's what you guessed? Well, you don't, but you could run a vibrational frequency analysis calculation, and if your guess was wrong and it really wants to break one of those symmetries, then you'll see an imaginary vibrational frequency corresponding to some asymmetric stretch mode or bend mode that will break the symmetry. And then if that happens, you can just follow that mode downhill a little bit, restart the optimization, and it'll be solved. So that is a issue you can just check for. Now, what else can I check? Well, your optimization should only take about 20, 30 steps or so. If it's taking, 200 steps, that's a sign something isn't set up very well. It could be that the guess Hessian is just very poor and the BFGS procedure has a hard time cleaning it up. If that's the case, you could run a Hessian calculation and then feed that to the optimizer. And there are various keywords to do this for various programs. And if it's a small enough molecule, that might be easy to do, especially if I drop to a lower level of theory. As long as that lower level of theory is reasonably trustworthy for the system, then that can get me a decent Hessian that might be better than the guess Hessian the program provides. And then that might fix everything for me. If you're looking for transition states, then it is particularly important to have a good guess for the Hessian because you need an accurate picture of the nearby potential energy surface to find that. If I have van der Waals complexes like methane dimer, then the potential surface tends to be very flat, and optimizing those systems is very difficult because it's hard to know how far to step because the surface is so darn flat. There it might be easier if you just by hand optimize certain coordinates, like the distance between the centers of mass of your two molecules, for example. You might just do maybe 6 calculations by hand at different distances try to find about where the minimum is, and then restart the optimizer there. Because if the optimizer is doing it, it can sometimes take just really inappropriate small step sizes because the gradient is so small. And it might take 100 cycles to get in the ballpark, or more, or it may never get there. Now you want to always check your output for any crazy results. What are the kind of crazy results you can get? Well, there are a lot of them. For example, if I'm doing excited electronic states, I might get negative excitation energies. And that is normally crazy, although it might be a sign that you weren't really at the minimum and there's some other global minimum below you. You might want to check your orbital energies. I do this very frequently. Normally, for a normal molecule, you want your occupied orbitals to have negative energies. That means they're stable and they like to be filled. And you want your unoccupied orbitals to have positive energies. If it's a cation, you might have a few of the unoccupied orbitals with negative energies, and that might be okay. That's just saying cations want more electrons. I do want to check my vibrational frequencies and make sure that they're not unphysical. So if I get an 8,000 wave number frequency, that's just crazy. And it's a sign probably that when I calculated my vibrational frequencies, I probably did it numerically by finite differences of gradients. And in one of those displacement calculations, I probably hopped up into some wrong potential surface. And that makes the energy change very discontinuously and suddenly, which could give me a really large, crazy-looking frequency. So probably one or more of your displaced geometries has the wrong SCF solution. If you are concerned you might be on the wrong SCF solution for whatever reason, you can run what's called a stability analysis. Many programs have this. It'll calculate the second derivative of the energy with respect to orbital rotations, rotating one orbital with another orbital. And if you find any imaginary eigenvalues in the stability analysis, it's a sign you're at some unstable SCF solution, and then you want to just walk downhill. A lot of the programs will have eigenvector following, and you want to walk downhill in that orbital rotation space to find a local minimum. Unfortunately, stability analysis won't distinguish whether you're at a global or a local minimum in wave function space, but it will at least let you know if you're at one of these unstable solutions. Now, orbital occupations. This is an issue that comes up if I have small molecules with high symmetry, which can happen, especially if you're a starting quantum chemist and you're doing some pedagogical projects. If I have a program that uses symmetry or knows about symmetry, then they'll tend to guess what the electron occupation is in terms of how many electrons go in what irreducible representations. So in the water molecule, it'll guess, hopefully, that I have, three pairs of electrons in A1 orbitals, one pair in a B1 orbital, and one pair in a B2 orbital. If I have high symmetry molecules or big basis sets, sometimes the program will guess something wrong. Like it might think, oh, I've got 2 electrons in A1 and 1 in B1 and 1 in B2 and 1 in A2. And if it guessed that for water, it would be wrong. But then the problem is that the program kind of gets locked in this kind of local minimum and has a hard time finding that there's a lower energy solution where I pop electrons out of one symmetry irrep and put them in another one. I could try to do an SCF stability analysis to check this, but it won't necessarily check it because it might actually be a local minimum, even though it's not the global minimum in orbital rotation space. Sometimes if this happens, you'll see in your output that I have electrons in orbitals with positive energies, or maybe more likely unoccupied orbitals with negative energies. And that's saying that unoccupied orbital with a negative energy really wants electrons. Probably that's a sign you should have put the electrons in that orbital and not in this other orbital. Some of these programs that know about symmetry, you can manually give it the irreps of the occupied orbitals, and that's a solution if you know enough group theory to be able to do that. Otherwise, sometimes running the initial calculation in a small basis set like STO3G, you're a little less likely to hop on one of these wrong solutions, and then you could feed that density into your true calculation with a bigger basis set, and that might help you avoid it. And then finally, I'll just mention again this potential issue of multi-configurational nature. We mentioned that diradicals, for example, can be dangerous with standard quantum chemistry methods because they assume the dominance of one electron configuration. But what if you're in a situation where you're not sure if you have potential near degeneracies of different electron configurations? Maybe I'm in some transition state where I'm breaking some bonds and forming some bonds, and I'm not sure if the bond breaking and bond forming processes will allow another electron configuration to have similar energy or not. In that case, there are some techniques you can use to try to diagnose a potential multi-configurational nature of the system, and I'll just mention a couple of them here. The first off, the simplest one is if I do an MP2 or couple cluster calculation, I can just look at my biggest T2 amplitude. That's the coefficient that goes in front of those excited determinants or substituted determinants in the total wave function. And if that coefficient is around 0.1 or less, it's probably fine, and you can use your standard single reference methods. But if it's, say, 0.2 or bigger than that, that might be a sign that I have some multi-reference nature to the problem. Similarly, there's something called a T1 diagnostic. This was invented by Tim Lee at NASA. And if I get this out of, say, a couple cluster calculation, and it's greater than 0.02, that's a sign that I may have a problem with the multi-configurational nature of the wave function, and I should be a little careful. Now, if there is a multi-reference nature or multi-configurational nature to the problem that I'm studying, what do I do? Well, the right solution is to use a multi-configurational or multi-reference approach like MCSCF, CAS-SCF, or CAS-PT2. Unfortunately, these are harder to use because they require you to pick an active space, and you have to have some expertise to know how to pick an active space appropriately. So they're not black box methods, but that would be the appropriate way to solve those problems. Well, with that, that's my practical advice for setting up quantum chemistry calculations and for analyzing whether anything has gone wrong. I hope you find this helpful, and I wish you good luck in your quantum chemistry adventures.
Where's Onyx? Oh, there she is.